Welcome students, I am Tanmoy. I welcome you all in my channel Chemistry and History of Molecule. So today we are going to discuss a unique type of molecule, or specifically say a different type of chemistry. And in reality, actually if you ask me, is it important for exam? I don't think so it is that much important for exam. But it is important for the satisfaction of the hunger of surprise in chemistry. Means, is such type of chemistry possible? Means, wow. Means, after reading this, you feel wow. Wow chemistry. So I consider this is a wow chemistry. So today we will discuss about Schlosser Base or Schlosser Base. Actually, this is a super base. So previously I have uploaded 2 videos about super acid. So in this context, in this direction, today I shall explain about super base. Okay, what is the meaning of super base? As like super acid, they are extremely acidic. Similarly, super base means extremely basic. Okay, so let's start. So in this context, actually, this Schlosser base is categorized as a mixture of alkyl lithium and potassium alkoxide. The simple question comes in this context, why? Why this mixture is needed? Because we know that these alkyl lithium are very strong base. Very strong base, like butyl lithium. And among that, if we think that this T-butyl lithium is more basic than N-butyl lithium. This we have already read. These are extremely basic. So what is the point of making this reagent? Second, this is a mixture of alkyl lithium as well as potassium alkoxide. Potassium alkoxide is not a strong base that much. So how this mixture can produce a stronger base compared to this alkyl lithium? That is the most important question. And today's talk will mainly cover for a few points. For example, the basic concept, role of each reactant, solvents, and benefits for the chemistry. Okay, so let's start. So this is they are very basic. Basicity in this way, this is far more basic. So actually, if you think, scientists are always curious to make better. Like, we always try to make something new such that the whole society could be benefited from the effort. And exactly that is the main motivation to pursue research and such type of results are the consequence of this research. So, here what is happening? So, if you mix Rl and KOR, it produces a very strong base, and the strong means it can deprotonate. It can deprotonate even toluene, benzene, or alkene. In this context, never say alkyne or specifically terminal alkyne, because terminal alkyne protons are sufficiently acidic. Toluene, benzene, that you have already read. Bule means N-bule plus sorry about my voice because of cold. So what happens? We know that this negative charge attacks here, and after that what it resulted? This resulted metal exchange. This is lithium. This is actually you can say plus minus in this way also you can explain. Plus BuBr. Okay, so for that you need halogen. So in this case, advantage you can do it directly, but these also has some disadvantages also. What is the disadvantages? Extreme reactivity. Because every achievement comes always in the cost of something, and that is extreme reactivity. So this is the advantage. And now, why alkene? Means what is the advantage? Normally if you take an alkene, normally if you take an alkene, say for example this is CH3. So what is expected? If you put butyl lithium, there could be many things possible. Even addition on the double bond possible, and that is one of the basic concept for butyl lithium mediated anionic polymerization. But if you use this Schlosser base, it will selectively abstract allylic proton. Okay, so that is another thing. Means that this is capable to abstract proton whenever it can. So this is the background of this is the background and proof of the extreme reactivity of this reagent compared to the parent one, butyl lithium. And let's learn a little bit about the tertiary butoxide. Tertiary butoxide, it is an alkoxide. So means I have written here alkoxide, better is tertiary butoxide. Let's take that example, O minus K plus. So this is an alkoxide having a tertiary butyl group, and we know this is a moderately strong base, not strong like this. But the question how this reactivity is achieved. So how it is improving, and that comes because of the agglomeration. So if you see the agglomeration of alkyl lithium. Okay, so in this context I want to mention that I have previously already uploaded a lecture about the agglomeration of butyl lithium and their unagglomeration or say monomer formation from using chelating ligand such that activity increases. So this remains in agglomerated form. So generally what is done, along with that some chelating agent like HMPA, Timeda, okay, are used, or ethylene glycol monomethyl ether. Let me give you a first example. This ethylene glycol, this is the ethylene glycol monomethyl ether. Okay, so what it can do? This can coordinate with the lithium. Similarly, Timeda tetramethyl ethylene diamine. N tetramethyl ethylene diamine. So they can also coordinate to the lithium center. So in this way, the polymeric butyl lithium forms a monomer, and see here the cation is stabilized. So what happens? The anion becomes bare, resulted in bare carbon ion. Okay. We know that carbon ion is not that much stable because electronegativity of carbon is in the middle. It is not electropositive, it is not electronegative. So what happens? That this bare carbon ion become more negative, and this concept I have explained in a better way, where the nucleophilicity, one video I have uploaded about nucleophilicity, where you find that DMSO, DMF, they solvate the salt, the cationic part of the salt, and anions like bromide, iodide, they become further reactive because the cation is solvated. So anion became free, bare, they can react even more efficiently. This is actually happens here, and this same concept is utilized here. How? So if you check the butyl lithium agglomeration, why this is agglomerated? Because in this way it gets stabilization. And if you compare this periodic table, lithium, sodium and potassium, okay, so plus if you compare, the size increases. So what happened? The consequently charge density also increases. Sorry, charge density decreases. Charge density decreases. Consequently, less polarizable. Okay. So now, if you consider lithium carbon versus potassium carbon, lithium plus carbon ion versus potassium plus carbon ion. Okay, and lithium plus oxygen anion versus potassium plus, let's consider this in this way, this oxygen anion, oxide. So this bond is stronger, these and this. Why? Because this is two, means second row matching. Here it is also second, third, fourth row, second row matching. So what happens if we think in this way? The overlap between this lithium plus and this is more. That is the background concept why this happens. But here this is less. So if you mix this potassium with butyl lithium RNi, what happens? What happens that actually there it's a probable explanation for its enhanced reactivity. Okay, it's a probability. So expected that this lithium plus is solvated by alkoxide. In this way, means solvated. Consequently, what is in the reaction medium? R minus and K plus. So we know that these, as I told, these and this overlap is not that much higher. So we can say by mixing we are solvating the cation, creating a bare anion as they are very less interaction. And in this concept you should know that if we think about the ionic nature, if cation is bigger, cation means plus bigger and anion minus molar half we have taken, then the packing is efficient. Why? For example, cesium fluoride, if we consider, we will say okay, fluorine is the second row element, cesium is at the end. Why this is that much? When you add an extra electron on fluorine, its size increases if significantly. Generally it is said that the hydride minus size is comparable to bromine. Okay, so here if it is smaller in size, so less polarizable. So and cation is higher, bigger in size, so charge density is less. That is also less capable to drag the electron density from the anion. Consequently, their packing is majorly ionic. Nothing is perfectly ionic. We can say 80% ionic nature, 70% that. But in this way, this strategy results in efficient packing and less polarization, means they prefer to remain ionic. That is the thing here also. So here potassium plus, you can see this is a bigger size compared to lithium. So right now this anion is stable, means it is perfectly ionic, more ionic compared to this. Now question, then actually this discussion indicates the reactivity is the consequence of potassium alkali. Okay, so if we take simple potassium alkali, then we can expect. But in reality, preparation of potassium alkali is difficult. Why I am saying? How butyl lithium is prepared? Butyl lithium is prepared by the reaction of, for example, butyl chloride plus lithium metal. It resulted in butyl lithium formation. But if you see sodium and or potassium, what happens? Sometimes they result in coupling, radical like Wood's reaction type. Okay, so first of all, preparation of alkyl potassium is difficult. Second of all, one another cross experiment was studied. So, and it was observed that their reactivity, this mixture's reactivity is different compared to that type of alkyl potassium. Okay, so in situ generated thing. So second, that why this reagent actually is a generally 1:1 mixture, and you can tune the reactivity by changing this also. Fine. So what we have understood, this is actually conclusion of this discussion. This is a mixture of lithium plus potassium plus means you can say X, Y. This actually before this is R minus, but after it generates something. So let's consider this an R minus, and along with that OR minus. So it is actually a mixture of these four. Okay, so this. Now question about the solvent. Generally such type of thing works done in inert solvent like hexane, pentane, like that. Why? As I told that they are reactive enough to react with aromatic solvent, aromatic molecule like benzene. And if they can react with benzene, it is expected they will react other aromatics also. So that is the reason. And another thing, you can perform such reactions in THF, but you can't store or prepare this in THF. That's the difficult. I shall explain on another video why butyl lithium does not stored in THF. Instead of that, it's stored in hexane or pentane. So, what is the benefit of the chemistry? So, the benefit of this chemistry is that preparation of a very strong base such that we can prepare selectively from a relatively means a benign CH bond, almost benign, to the corresponding carbon ion. And actually this reactivity is believed because of the potassium and carbon, because this lithium is, you can say, coordinated, stabilized because of this OR. Consequently, this alkyl anion and potassium anion performs this reaction. Okay, so this is an organic super base. So what we have learned? We have learned today about the Schlosser base, super base. And okay, I forgot one thing to mention. Why it is called Lickor super base? This is the name, Lickor, Lickor. LIC is alkyl lithium, lithium carbon. KOR means potassium alkoxide. Okay, so this is another information you should know. Okay, sorry friend, I forgot to give you example which I decided to give. So that's why I am adding this. So it may be may look like a little odd, but I am sorry for this mistake. Okay, so let's start. So see, this is a substrate reacted with this K plus O TBU plus butyl lithium. Okay, so this. So what happens? We know that such type of case will result in the active species this formation. Fine. So what is expected to have? So this Bu minus can abstract this hydrogen. Now you may ask the question why. I'll explain. This is OR, CH3, this is CH minus Cl. Why this is abstracted? Because this is attached to electronegative atom, and that argument is also applicable for this here. But the question, why not here? Here, although electronegativity of oxygen and electronegativity of oxygen and chlorine close around. Why? Because see, this oxygen has a lone pair, this chlorine also, but here the bond is, it is third row, it is second row, shorter bond, severe distance because of orbital matching. So what is expected that in this case produced carbon ion is relatively more stable compared to this. Second point, chlorine have energetically accessible vacant d orbital, so that chlorine can reduce through conjugation of an electron deficiency. This is the argument I am giving, but actually with respect to this, it's possible. So this is the logic I believe may be possible. Fine. So next step what happens? This CH leaves. And what this leaving of Cl minus resulting, this is a carbene formation. Okay. And next step, CH insertion happens, means this. And it forms a cyclopropane ring. So this is the application, one of the example of the reactivity of this Schlosser base. And along with that, since this butyl potassium case, please keep it in mind. Actually, butyl potassium, I forgot to tell you how to prepare. So it could be prepared from corresponding organosodium or organolithium reagent, but these are not that much used because this butyl lithium, this alkyl lithium are easy to prepare, stored and commercially available, and all the thing could be done using this. And another thing, got one modification. So organopotassiums are generally not attractive one. Okay. So this is the end of the discussion. Thank you all for listening my video. So see you in my next video. All the best. Stay happy. God bless you.